On December 21st, 2015, a 70-meter-tall rocket booster descended from the edge of space and landed upright on a concrete pad at Cape Canaveral. For 60 years, orbital rockets were disposable. SpaceX changed that with autonomous vertical landing. Today, we're exploring how they did it. With us are aerospace engineer Ryan Mercer and business analyst Dr. Anjali Kapoor.
The hard part wasn't getting to orbit, it was getting back. The Falcon 9's first stage separates, flips itself around at hypersonic speed, and performs a series of engine burns to slow down and steer. The key insight is that this entire sequence, from 100 kilometers up through re-entry to a soft landing, is entirely autonomous. No pilot, just software and hardware working in a perfect high-speed ballet.
Let us be precise about the economic disruption. The first stage booster constitutes roughly 70% of the total cost of a Falcon 9 rocket. By recovering and reusing this single, most expensive component, some boosters have now flown more than 20 times. SpaceX fundamentally altered the cost equation for accessing space. Launch prices plummeted and launch frequency soared. It created an entirely new market dynamic.
And this is the clever bit, the landing itself. An almost empty booster is so light that even one of its 9 Merlin engines at minimum power is too powerful to let it hover. So SpaceX engineered the engines to deep throttle, to dial their thrust way down. The booster then performs a hover slam, a suicide burn where it lights the engine just in time to reach zero velocity at exactly zero altitude. It's an incredibly difficult maneuver.
Now, consider how this engineering is enabled by the business structure. SpaceX practices extreme vertical integration, manufacturing an estimated 80% of its components in-house, aircraft's avionics. This is unlike the traditional aerospace model of relying on a vast web of subcontractors. It gives them immense control over cost, quality, and, crucially, the speed of design changes.
That control is vital for hardware like the grid fins. During descent, 4 of these waffle iron-like fins deploy near the top of the booster. They steer the rocket with incredible precision. Here is the hard part. They operate at hypersonic speeds, so aluminum would just melt. Each fin is forged from a single piece of titanium, a material choice dictated purely by the physics of atmospheric re-entry.
And this points to another radical departure, their development philosophy. The crucial point is that SpaceX applies a software-style iterative cycle to hardware. They build a version, fly it, and gather data. Failures are not seen as catastrophes, but as valuable data points that inform the next rapid iteration. This build, fly, learn loop is much faster than the traditional risk-averse aerospace approach.
That iterative loop perfected the closed-loop guidance software. The booster isn't following a pre-written script. Thousands of times a second, it senses its position and velocity, compares that to the target, and resolves the flight plan on the fly. It actively commands the engine throttle and grid fins to correct for wind, allowing it to land on a moving drone ship in the middle of the ocean.
This entire system, reusable rockets, low costs, high flight rate, created a unique opportunity. SpaceX became its own best customer. They created Starlink, a mega constellation of thousands of internet satellites. They use their own reused rockets to launch their own satellites, creating a powerful, self-reinforcing business loop. The demand they created justified the entire system they built. So, a revolution built on 3 pillars. First, mastering autonomous propulsive landing to make rockets reusable. Second, developing the specific hardware and software, from deep throttling engines to titanium grid fins. And third, a vertically integrated, iterative business model that even created its own launch demand. Ryan Mercer and Dr. Anjali Kapoor, thank you for breaking this down for us.